July 1st, 2020. A routine NASA scan triggers a global alert. An object is tearing through our solar system at 137,000 miles per hour. It's called 3I/Atlas, and it's not just another space rock. This interstellar visitor is up to 9 miles wide, shrouded in a strange carbon dioxide coma, and follows a path that defies the odds, raising grave doubts about whether we're witnessing a cosmic accident or something deliberately aimed our way. The last time something like this happened, we saw Oumuamua slip away before answers emerged. Now, with a new Oumuamua on our doorstep, astronomers are racing to decode its true nature. What or who is guiding this colossal traveler, and does its arrival signal a far greater mystery? At 2:13 a.m. UTC on July 1st, 2025, a faint, fast-moving speck appeared in the nightly data stream from the ATLAS telescope at Rio Hurtado, Chile. The system's automated detection pipeline flagged the object as A11PL3ZA, just another candidate among thousands surveyed each night. But by sunrise in Hawaii, the ATLAS team noticed something off. The object's apparent motion was too rapid, its path skewed from the slow, predictable arcs of main-belt asteroids. Within hours, the Discovery Alert rippled across the Minor Planet Center's global network, drawing in survey teams from Pan-STARRS, the Zwicky Transient Facility, and Catalina Sky Survey. While most flagged objects fade into statistical noise, this one demanded immediate attention. Its velocity, measured at 137,000 miles per hour relative to the Sun, placed it far outside the gravitational grip of our solar system. For comparison, most near-Earth asteroids crawl along at less than a tenth that speed. The initial orbital solution, based on just a few hours of data, already suggested a hyperbolic trajectory, a telltale signature of something not born in our neighborhood. Verification moved at a pace rarely seen in astronomy. Quanji Ye's automated cross-checking program at the University of Maryland pulled up pre-discovery images from the Zwicky Transient Facility, extending the observational arc from hours to days. That widened window allowed orbital analysts to refine the trajectory with unprecedented speed. By midday July 2nd, Robert Seaman at the Catalina Sky Survey had circulated an internal alert. The orbital eccentricity was well above 1, confirming the object's interstellar status. The designation changed overnight. A11PL3Z became 3I/ATLAS, the third confirmed interstellar object ever recorded. For the ATLAS team, led by John Tonry and Larry Denneau, the realization struck hard. Their system, designed for planetary defense and routine asteroids, had detected a visitor from another star system. The object's inbound path cut against the dense star fields of the galactic center, a region most surveys avoid because the background is so crowded. Yet ATLAS's persistent sky coverage proved decisive. Larry Denneau later noted that the object had been visible in their archives since June 5th, but its faintness and the confusion of background stars delayed its recognition. Within 24 hours, NASA's orbit determination experts confirmed the boldest suspicions. 3I/ATLAS was not bound to the Sun. Its trajectory, inclination, and velocity marked it as a true interstellar wanderer, following a hyperbolic path that would carry it through the heart of the solar system and then back out into the darkness between the stars. The news spread through astronomers' inboxes and Slack channels worldwide, triggering an unprecedented, coordinated response. Telescopes from Mauna Kea to the Canary Islands began tracking the object, while space-based assets like Hubble and JWST were petitioned for urgent observation time. The discovery's implications settled in quickly. Unlike Oumuamua, which was detected only as it was leaving, 3I/ATLAS had been found inbound, with months to go before perihelion. For the first time, astronomers had a chance to watch an interstellar visitor approach the Sun in real time. The global network of survey telescopes, a TLAS, pan-stars, ZTF, had done what once seemed impossible. They caught a messenger from another world while it was still within reach. The question now was not just how fast or how bright this object was, but what secrets it might reveal as it swept closer to the inner planets. 3. I/Atlas dwarfs every expectation set by its predecessors. Early ground-based estimates painted it as a possible behemoth, 10, even 20 kilometers wide. But high-resolution images from the Hubble Space Telescope in July 2020 forced a dramatic revision. The nucleus, stripped of its deceptive shroud of dust and gas, measures no more than 5.6 kilometers across. Most likely it's smaller still, perhaps less than a single kilometer in diameter, a size now echoed by multiple independent studies. Yet, even at the lower end of these estimates, 3Y/Atlas stands as the largest interstellar object ever observed, outclassing both Oumuamua, Oumuamua, and Borisov by a wide margin. The scale of its coma is even more staggering. Hubble and the Gran Telescopio Canarias revealed a halo spanning over 26,000 kilometers, twice the diameter of Earth. This immense cloud isn't just an optical trick, it's a chemical signature. The James Webb Space Telescope's NIRSpec instrument, pointed squarely at the heart of the comet on August 6th, delivered a result that stunned the scientific community. The coma is dominated by carbon dioxide, with a carbon dioxide to water vapor ratio of 8:1. For comparison, most solar system comets barely reach a ratio of 1:3. Here, the carbon dioxide emission alone is measured at 129 kilograms per second, while water vapor lags far behind at just 6.6 kilograms per second. This chemistry is not just unusual, it's unprecedented. No comet, interstellar or local, has ever shown such a lopsided dominance of carbon dioxide at this distance from the Sun. The SphereX mission confirmed these findings, mapping a vast carbon dioxide coma stretching hundreds of thousands of kilometers with little sign of a comparable water cloud. Ground-based spectrographs added to the chemical portrait, picking up traces of carbon monoxide, carbonyl sulfide, and even atomic nickel vapor, molecules familiar from solar system comets, but never in this proportion. The implications are profound. Such a high carbon dioxide content suggests a birthplace far from the warm, water-rich regions of a planetary system. 3I/Atlas may have formed near the carbon dioxide ice line in its home protoplanetary disk, or perhaps it endured eons of radiation in interstellar space, selectively erasing water ice while leaving carbon dioxide behind. The presence of fine-grained, likely amorphous, water ice in the coma, detected by JWST and SWIFT, hints at a nucleus that has remained frigid for billions of years, preserving a chemical fingerprint from a time before our Sun was born. The object's shape and rotation only deepen the mystery. Unlike Oumuamua's dramatic tumbling and brightness swings, 3V/Atlas rotates every 29 hours with barely a flicker, just 0.2 magnitudes of variation. This stability points to a more spherical form, a compact core lurking within its colossal veil. All of this, wrapped in a cloud of dust and ice, now races toward the inner solar system. Every new observation challenges familiar categories and pushes the question, is this the product of a strange, ancient chemistry or something else entirely? Tracking the path of 3I/Atlas reveals a sequence that has stunned orbital dynamicists. Within a span of just 6 months, the object will pass near 4 major planets: Mars, Venus, Earth, and Jupiter. Each encounter separated by precise intervals and distances that seem almost too coordinated to be the result of chance. On October 3rd, 2025, 3I/Atlas comes within 0.19 astronomical units of Mars, a distance of about 28 million kilometers. Less than a month later, it reaches perihelion, its closest approach to the Sun, but does so while positioned almost directly behind the Sun as seen from Earth. By November 3rd, it sweeps past Venus at just 0.65 astronomical units, and on December 19th, it passes Earth at 1.80 astronomical units. Never coming close enough for concern, but close enough to be tracked by every major observatory on the planet. The sequence concludes with a flyby of Jupiter at 0.36 astronomical units on March 16, 2026. Simulations run by orbital mechanics teams at JPL and independent groups in Europe confirm that this trajectory is not only hyperbolic, but retrograde, tilted 175 degrees to the plane of the ecliptic, slicing through the solar system in the opposite direction of the planet's motion. For an object entering from interstellar space, such retrograde alignment is rare, but not impossible. What elevates this path from unusual to extraordinary is the near-perfect alignment with the ecliptic, placing 3I/Atlas on a plane just 5 degrees off from the planetary orbits. Statistically, a random interstellar object would be expected to arrive from any direction, yet this one approaches as if it were aiming for the solar system's crowded midsection. The odds of such a sequence occurring by chance have been calculated using Monte Carlo simulations and n-body integrations. Researchers at the Harvard-Smithsonian Center and the University of Cambridge generated thousands of synthetic interstellar trajectories, each with randomized approach vectors and velocities matching the observed distribution from known objects. In these simulations, the likelihood that a single interstellar object would pass within a comparable distance of 3 or more major planets in a single transit while maintaining a retrograde, near-ecliptic orbit is less than 0.005%. In other words, for every 20,000 objects entering the solar system from interstellar space, only one would be expected to follow a path like this by chance alone. This improbable geometry has prompted some to wonder whether gravitational focusing or other natural mechanisms could nudge interstellar objects into such coordinated encounters. However, the simulations account for the sun's motion through the galaxy and the gravitational influence of the giant planets, and still the numbers remain stubbornly low. The sequence, Mars, perihelion, Venus, Earth, Jupiter, unfolds with a precision more reminiscent of a planned mission than a random visitor. Celestial mechanics offers no easy explanation for this pattern. The retrograde, nearly coplanar trajectory, combined with a series of planetary flybys, stands apart from the millions of minor bodies catalogued to date. For those who study the choreography of planetary encounters, 3I/Atlas presents a puzzle, an object whose path through the solar system seems to defy the odds, raising the unsettling question of whether pure chance can account for such an engineered course. In October 2017, astronomers at the Pan-STARRS 1 telescope in Hawaii detected a faint, fast-moving object streaking across the sky. The discovery, catalogued as 1I/Oumuamua, marked the first time an interstellar visitor had been observed passing through our solar system. At first glance, it seemed unremarkable, a dim point of light fading quickly as it receded from the sun. But as data accumulated, Oumuamua's peculiarities became impossible to ignore. The object's light curve, measured over several weeks, revealed dramatic swings in brightness, sometimes by a factor of 10 in just a few hours. This pattern suggested an elongated shape, at least 5 to 10 times longer than it was wide, unlike any asteroid or comet previously catalogued. Yet, despite its rapid motion and tumbling spin, no tail or coma appeared. Sensitive instruments searched for even the faintest trace of dust or gas, but found nothing. The absence of outgassing, especially at its closest approach to the sun, defied expectations for a body presumed to be rich in ices. As Oumuamua sped away, astronomers noticed another anomaly. Its trajectory deviated slightly from the path predicted by gravity alone. The object was accelerating, but not in a way that matched the subtle pushes and pulls of planetary encounters. Typically, comets experience such changes when jets of vapor erupt from their sunlit sides, but Oumuamua showed no evidence of this process. The non-gravitational acceleration, measured with precise astrometry, was real. yet its cause remained hidden. These mysteries provoked a flurry of speculation. Some researchers proposed that Oumuamua was a fragment of a disrupted planetesimal, its elongated form shaped by tidal forces or violent collisions in another star system. Others suggested more exotic origins, a low-density fractal aggregate, or even a hydrogen iceberg, rapidly sublimating in the warmth of the sun. But the lack of detectable gas, the strange acceleration, and the object's fleeting presence left every theory with unanswered questions. A small but vocal group of scientists, led by Harvard astronomer Avi Loeb, advanced a more radical possibility. They argued that the combination of unexplained acceleration, extreme shape, and inert surface might point to an artificial origin, a probe, perhaps, sent intentionally from another civilization. While most astronomers considered this scenario unlikely, the absence of a clear natural explanation kept the debate alive. Oumuamua, true to its Hawaiian name, meaning a messenger sent from afar, left as many questions as answers. The encounter with Oumuamua set a precedent that would shape every subsequent interstellar discovery. Its brief passage, detected only after it had already swung past the sun, meant that critical observations were missed. Spectroscopy, high-resolution imaging, and targeted searches for outgassing all came too late. By the time telescopes could focus on it, the messenger was already vanishing into the dark. The lesson was clear. The next time an interstellar object appeared, astronomers would need to act faster, observe longer, and question every assumption. The memory of Oumuamua's silent, enigmatic transit still lingers, shaping the questions now being asked of 3I/Atlas as it sweeps toward the inner solar system. Harvard astrophysicist Avi Loeb has never shied from controversy, but with 3I/Atlas, his arguments have drawn even sharper lines. In July 2025, Loeb introduced his own metric, the so-called Loeb scale, to rate the likelihood that an interstellar object might be artificial. He placed 3I/Atlas at a 6 out of 10, later revising it to a 4 as new data arrived, equating to a 40% chance of technological origin. This ranking stands in stark contrast to the consensus among planetary scientists who overwhelmingly favor natural explanations. Loeb's reasoning centers on the object's trajectory and timing. He points to the path of 3I/Atlas, a solar occultation with perihelion occurring on the far side of the Sun from Earth. According to him, this is not just a statistical oddity. It could be a deliberate maneuver. As Loeb frames it, if an extraterrestrial probe wanted to approach the inner solar system while avoiding detailed observation, hiding behind the Sun during closest approach would be the perfect tactic. The geometry not only shields it from Earth's telescopes at a critical moment, but also offers a launch window for deploying smaller devices, what he calls gadgets, to other planets, all while remaining out of sight. Backing up these suspicions, Loeb and collaborators Adam Hibbard and Adam Crowell published a paper outlining the statistical improbability of the trajectory. Their calculations suggest that the odds of an interstellar object hitting such a sequence of planetary alignments and a near-ecliptic retrograde orbit are less than 0.005%. They argue that natural gravitational dynamics alone rarely produce such precision. Loeb takes the speculation further, suggesting that after perihelion, 3I/Atlas might attempt a Jupiter-Oberth maneuver, a powered flyby using the gas giant's gravity to alter its course, potentially remaining bound to the solar system. This is a maneuver familiar to human spaceflight engineers, but in this context, it becomes a hypothetical sign of intent. Loeb's hypothesis is not that 3I/Atlas is definitely a probe, but that its path and timing are suspicious enough to warrant serious consideration. In his view, the combination of trajectory, occultation, and the possibility of a gravitational assist at Jupiter nudges the object up his scale toward the realm of the artificial. Yet, even as he lays out these arguments, Loeb concedes that extraordinary claims demand extraordinary evidence. So far, 3I/Atlas has not displayed controlled maneuvers, artificial emissions, or any clear sign of non-natural origin. For now, its rating on the Loeb scale remains provisional, a reflection of how much is still unknown and of the tension between statistical anomaly and physical proof. Cosmic silence is not an accident. In the vastness of the galaxy, every star hosts its own secrets, yet the sky remains mute. This is the essence of the dark forest principle, first imagined by Liu Cixin. It proposes that every civilization, fearing detection, hides in the cosmic shadows, because to reveal oneself is to risk annihilation by a more advanced, unknown neighbor. The arrival of 3I/Atlas now stirs this quiet. Its improbable path, threading the orbits of Mars, Venus, Earth, and Jupiter, raises a question that cannot be answered with orbital mechanics alone. If intelligent life is common, why does the universe remain so still? Is every world watching, listening, and calculating the risks of being seen? For astronomers, the silence is not reassuring. It suggests the galaxy may be filled with watchers, each wary of revealing their presence. The trajectory of 3I/Atlas, with its precise planetary alignments and solar occultation, echoes the logic of the dark forest. Observe without being observed, learn without leaving a trace. In this view, cosmic quiet is not a sign of emptiness, but of caution, a survival strategy played out on a galactic scale. Now, as 3I/Atlas sweeps past, the question shifts from what it is to what it means. Are we witnessing a natural wanderer or a visitor practicing the same careful restraint? The silence persists, but the mystery deepens. What would it take for us to break that silence? Should we call out? Or is it wiser to keep watching quietly from the dark? The next move, for the first time, might be ours to decide. On July 1st, 2025, astronomers confirmed 3I/Atlas as only the third known interstellar object to visit our solar system, traveling at 137,000 miles per hour and measuring up to 9 miles across. Unlike any comet previously observed, its coma is dominated by carbon dioxide, a detail confirmed by the James Webb Space Telescope. Orbital simulations place the odds of its multi-planet flybys at less than 0.005%, raising new questions about its path and origin. Yet, as with Oumuamua in 2017, direct evidence of intent or artificial construction remains absent, and much of the object's true nature is still unknown. Scientific debate continues, with peer-reviewed analysis and open preprints fueling both caution and curiosity. Today, 3I/Atlas stands as a reminder of how much remains undiscovered in our cosmic neighborhood. What is clear, interstellar visitors are not theoretical. They are real, they are rare, and their secrets challenge what we know about the universe.